Here are two examples of linear equations in two variables. If you remember, a linear equation in two variables has a multitude of solutions. They are ordered pairs. First is the x value, second is the y value in that ordered pair. And those ordered pairs make the statement true. So in this instance, there are a number of ordered pairs, x and y, that will make the left side of the equation 14. In fact, there are an infinite number of solutions to that equation. There are an infinite number of solutions to this equation. There are an infinite number of ordered pairs, x and y, that if we plug them in, the left side of the equation will become -7. If you recall, in order to express that entire set of solutions, we draw a graph by taking some of those ordered pairs, plotting them on our rectangular coordinate system, and we find that those ordered pairs make a straight line. The picture, the graph of the solution set of a linear equation in two variables is always a straight line. Now, if we were to graph the solution sets of these two equations, one of three things could occur. Either the lines could intersect in one point, or the lines would not intersect at all, and the only way that could happen is the lines would have to have the same slope. They would have to be parallel lines. Or the lines could be superimposed one on top of the other. Let's consider the situation where the lines intersect in only one spot. That point where the lines intersect, let's suppose our lines looked something like this. Let's suppose one line looked like this, the other line looked like that. That one point where the two lines intersect would be a solution that happens to be a solution for both equations. Remember, that's what the line pictures. Any point on the line is a solution for the equation related to that line. So if we had these two lines intersecting in one point, that would tell us that that xy point had to be a solution for both equations. So we might ask ourselves the question, how could we determine what that common solution was for these two linear equations in two variables? Sometimes we call these two equations together a system of linear equations. In this case, it would be a system of linear equations in two variables. So this point that is a solution for both of the equations would be what we would call the solution for the system of linear equations. The question then is, how do we find that solution? Well, I suppose this would be one way we could find that solution. We could graph the solution set for each equation and find the point where those lines intersect. If we had a good graphing tool, such as a graphing calculator, or perhaps we would go out online and find a graphing tool that we could use, we would be able to graph those two lines and get that point of intersection, that point of common solution for the two equations. But what if we don't have that type of tool available to us? Is there some way we can find that solution algebraically? Because it might be a situation that without a graphing tool like that, we would have a hard time determining exactly what that point of intersection was. If the point of intersection involved fractions rather than strictly whole numbers, that would make it difficult to read from a graph. So there must be some method that we can use to solve this system of equations algebraically, so that we can determine that one point of intersection, that one point, that one common solution that both equations share. And that common solution is what we call the solution to the system of linear equations. That's what we want to learn now in this series of videos. We want to learn an algebraic procedure we can follow to find that point of intersection, that point of commonality, that solution of commonality for those two equations, if it exists. Should the two equations be parallel, then no common solution would exist. And the other interesting situation, should the lines lie one on top of the other, then every solution for one would be a solution for the other. And we'll take a look at those special circumstances a little bit later in our video series. But we want to start with a video that looks at how do we algebraically find that solution of commonality, that solution for this system of linear equations in two variables.